Hi everyone, my name is Marilyn Tournay and I am going to be your professor for Chem 307, Quantitative Analysis. This is the book that we're going to be using. It's titled Exploring Chemical Analysis. It's the 5th edition and it's by Daniel C. Harris. This is the first of many videos that you will be watching this semester. I hope you enjoy them. Alright, let's get started. These first lectures and videos are just going to be a review because this is stuff that you should have gone over in your previous chemistry or math classes. So just to get your feet wet from chapter 0, we're going to go over the analytical process. Now I'm going to talk about these independently, but it's broken down into simple steps. So what is your question? You have to select the procedure that you're going to use to answer your question. You have to take your sample, and sometimes, most of the times actually, you will have to prepare that sample because it just can't go in the way that you obtained it. Then you make your analysis, and that could be anything from, measuring the concentration, how many replicates do you need, and then after you do all of that, you have to interpret your results. So all that is very important to each part of your analytical process. We're going to talk about really quickly what the difference is between quantitative and qualitative analyses, and also what is the purpose of a calibration curve. All right, let's get started. A typical question you might encounter in a laboratory is how much caffeine is in a chocolate bar? Now that might seem like an easy question to answer, but actually it's not, because there is a lot of stuff in chocolate. I mean, there's fat, there's sugar, they might have put some additives in it. So to answer such a general question like how much caffeine is in a chocolate bar is really, really difficult. So the first step of an analytical process is always to search the literature. I mean, you don't want to reinvent the wheel. And more than likely, someone somewhere has done at least a portion of what you're trying to do. And of course, I understand that there might be an instance where, you're doing something completely new, so you can't find anything in the literature, but you always start there. Always, always, always. And especially for this example, someone has done something. So you could use scientific resources like SciFinder. There's many others, but they use SciFinder and they search through chemical abstracts by using keywords. They used chocolate and caffeine. I mean, you can use anything that you think might be helpful. You can use analyze caffeine or analyze chocolate to try and pick up articles that are dealing with what you're trying to do. They concentrated on one article which was titled High Pressure Liquid Chromatographic Determination of Theobromine and Caffeine in Cocoa and Chocolate Products. I mean, theobromine is just a precursor to caffeine, but this is exactly what they're trying to do. They're trying to analyze how much caffeine is in a chocolate product. It's kind of like a recipe. It kind of gives you a recipe to bake your cake. They can get answers such as, well, what type of instrument should I be using? How much sample should I take for this analysis? How am I going to interpret my results? All that stuff can be answered by just looking through the literature and helping yourself out. And yes, of course, this might be a little time consuming searching through the literature, but in the end, it'll save you time. So once you know what you need to do, the next step is to get a sample. The most important thing here is that your sample must be representative of your entire batch. Okay, because if you're going to start making universal statements about how much caffeine is in chocolate, you better make sure that what you're publishing is correct. You don't want your data to be criticized by the scientific community. What the students did in the book is they went to their neighborhood store and they bought a bunch of different chocolate bars. Okay, and of course they're going to analyze each of them. And you have to analyze each chocolate bar several times because you want to make sure that the caffeine content in that one chocolate bar is the same throughout that one chocolate bar. And of course, then they would compare all of the different chocolate bars at the end. But you've got to make sure that what you're doing here makes sense. Another question that you might want to answer is your sample a homogeneous sample or a heterogeneous sample? And if you had something like a pure chocolate bar, well, that would be a homogeneous sample because it's the same throughout, or should be the same throughout. But if you had something like a macadamia nut chocolate bar, that's of course a heterogeneous sample. You've got macadamia nuts in one portion, and you've got chocolate in the other portion. But the most important thing is, again, you got to get a representative sample. It should be as small as possible, right? Because in the real world, we don't have tons and tons of sample to work with. So your sample should be as small as possible, but it should be representative of what your batch is. The next step in the process is your sample prep. This is probably the most tedious part of the process, but probably one of the most important. So from the literature, the two students noticed that the procedure they were looking at calls for weighing a quantity of chocolate and extracting the fat from the chocolate. Apparently, fat interferes with their caffeine analysis, so they have to remove it first before they can actually analyze their sample. You have to use a solvent to try and extract all of the fat from the actual chocolate. So what they did is they took a chunk of chocolate, they sliced it up into thin pieces, and then they ground it up with a mortar and pestle. You have to realize why they're trying to do that. Remember, you're using a solvent to try to remove all of the fat from the chocolate. It's a lot easier for a solvent to penetrate a solid if it's ground up into fine particles than it would be if it was a big, huge chunk of chocolate just dumped into a beaker of solvent. So they ground it up, and then they took their ground up pieces of chocolate and they weighed it just to make sure that they knew how much they started with. And they put the chocolate into a 15 ml centrifuge tube, which I'm showing you right here. And then they added 10 milliliters of an organic solvent. That organic solvent was petroleum ether. A good question to ask yourself is, why did they use an organic solvent or a non-polar solvent versus a polar solvent to try and extract the fat? You have to also realize that caffeine and theobromine, which are the things that they're trying to analyze, are not soluble in this organic solvent. That's a clue. So they put the cap on the centrifuge tube and then they shook it really, really hard to try and make a suspension of the solid in the solvent. Then they actually took that centrifuge tube and put it into a centrifuge to try and pack all of that solid down to the bottom. Think of a centrifuge like the gravitron in the fair. It kind of just pushes everything all to the side and down. So you pack all of the solid particles down to the bottom of the tube, and then what you're left with is that supernatant liquid, which actually includes the fat that you're trying to remove. So then you take that liquid and you decant it off. Decant just means to pour off. So you pour it off really carefully, and you do that process a couple times. The students did it 2 more times just to try and ensure that they've extracted as much fat as possible from that chocolate sample. Now, any residual solvent that might be left in that chocolate after they do these extractions, they try to remove it by heating the uncapped centrifuge tube in a beaker of boiling water. Once they've removed the residue solvent by boiling the centrifuge tube in a beaker of boiling water, they go ahead and weigh the centrifuge tube plus the content of the defatted chocolate residue, and then subtract the known mass of the empty tube. That way they know what mass of chocolate they actually have in their tube. The next step is to quantitatively transfer the fat-free chocolate residue to an Erlenmeyer flask and then dissolve it in water for chemical analysis. Quantitatively transferring means that you completely transfer your entire analyte sample. In this case, the analyte is your defatted chocolate, which includes your caffeine and your theobromine. If you don't transfer everything that's in that tube, then the final analysis is going to be incorrect because you're not including everything that you have in your sample. So to perform this quantitative transfer, they actually add a little bit of pure water into the centrifuge tube and stir it and heat it to kind of dissolve and suspend as much of the chocolate as they possibly can, and then they pour that into a 50 ml Erlenmeyer flask, which I'm showing you right here. Now they repeated that procedure several times with fresh water, obviously, to ensure that every last bit of chocolate was transferred from the tube into the Erlenmeyer flask. Once they are pretty sure that they've got everything from the centrifuge tube, they actually bring the volume up to about 30 mils, and they heat the flask in a boiling water bath to extract all of the caffeine and the theobromine from the chocolate into the water. Before they can actually inject the solution into a chromatograph or into an instrument for chemical analysis, they actually have to clean it up a little bit more. That slurry of chocolate residue and water contained really small solid particles that would for sure clog your instrument, so you can't have that. So what they do is they put a portion of the slurry into a centrifuge tube and centrifuge that down to pack that solid as much as possible. They did that about 5 times, and they noticed that the actual supernatant liquid wasn't getting any clearer, so they just went ahead and withdrew the supernatant liquid from the centrifuge tube into a syringe and filtered it into a fresh centrifuge tube. That filtered solution then actually contains the dissolved analytes for injection into your chromatograph. That entire process that we talked about is quite tedious, and it's all part of the sample prep. In this case, you had to remove the fat from the chocolate so that we can actually analyze the caffeine and the theobromine. Next step is going to be the analysis. The next step was to inject solution into the chromatography column, which basically separates the analytes and measures their quantity. The column that you see here is packed with tiny particles of silica dioxide, to which long hydrocarbon molecules are attached to. The separation of caffeine and theobromine by chromatography is really simple. Basically, caffeine is more soluble in theobromine in the hydrocarbon layer. So that means that caffeine is actually retained more strongly in the column and moves through the column more slowly. It basically sticks to the column much better than the theobromine does, so it comes out later. So what you see here in number 4 is the theobromine coming out first, and then that caffeine coming out a little bit later. The analytes are actually detected at the outlet by their ability to absorb ultraviolet radiation. As the compounds actually come out from the column, they absorb this radiation that's emitted from the lamp in the figure here that I'm showing you on the left. The graph of the detector response versus time, which is on the right, is called a chromatogram. And you can obviously see that the theobromine and caffeine are the major peaks in the chromatogram. Any other small peaks you see there are probably just any other components that might have been in the aqueous extract of the chocolate. So there's two types of analysis. There's a qualitative analysis and a quantitative analysis. Identifying what an unknown is, just like basically what it is, theobromine, caffeine, that just tells me a qualitative analysis. If I want to know how much of that analyte is in that sample, that's a quantitative analysis. Quantitative analysis is obviously a little bit better, but it takes a little bit more to get that answer. I want to talk about calibration curves next. If I have a small concentration of something, it should give me a small response. If I have a large concentration of something, it should give me a larger response. And a graph that shows a detector response as a function of analyte concentration is called a calibration curve or a standard curve. Let's talk about that next. To construct a calibration curve, you use standard solutions containing known concentrations of pure analyte and inject them into the column. In this case, we're going to use pure theobromine and pure caffeine to inject into the column. And we're going to measure the resulting peak heights. As I said in the previous slide, the lower the concentration, the lower the peak should be. Figure on the left shows a chromatogram of one of the standard solutions. And of course, the figure on the right shows the calibration curves made by injecting these solutions. This particular example has 4 different samples, one at 10, 25, 50, and 100 micrograms of each analyte per gram of solution. So once you actually make these curves from pure standards, you can actually use this calibration curve to figure out what the concentration of your unknown is. On the figure, it shows that if the observed peak height of theobromine from an unknown solution is at 15 centimeters, then the concentration should be about 76.9 micrograms per gram of solution. The next step in the analytical process is to interpret your results. The table on the top shows the results for the dark and white chocolates that they tested. The quantities found in the white chocolate are only about 2% as great as the quantities in the dark chocolate. You can see that the table also gives you the standard deviation of 3 replicate measurements for each sample. We're going to talk about standard deviation in the next videos, and we're going to talk about accuracy, reproducibility, error analysis, all of that stuff. For right now, let's just concentrate on what they got. For theobromine in the dark chocolate, the standard deviation is about less than 1% of the average. So we say that the measurement is actually really good. It's very reproducible. But the theobromine in the white chocolate, the standard deviation is a lot higher. So the measurement actually that they took there was not very good, not very reproducible. So after all of that work, all these students did is actually find how much caffeine is in one chocolate bar. It would take a huge amount of work to sample all the chocolate bars in the world and make this into a concise table. But as you can see here, the table on the bottom compares the results from different kinds of analysis of different sources of caffeine. One of the last steps that you also want to do is quality assurance. And by that, I mean, how do you assure that your data is correct? How do you assure that the methods that you did were properly done? One of the things you can do is add a known quantity of caffeine to your mixture and test it. Since you know how much you're adding, you should know what the response should be. So you could do that that, and that's called spiking. Or they could also maybe use other analytical methods to test it. You should be able to get the same type of response that you got from this method. Another thing you could do is maybe send it to outside labs and have them test it and make sure that they get more or less the same results. The analysis that you do in chemistry is meaningless unless you have collected the sample properly, you have taken measures to ensure the reliability of that analytical method, and you actually communicate your results clearly and completely. If you don't do those three things, then what you've done is completely pointless, and all the time that you've put in doesn't mean a thing. So I hope you've enjoyed your first video, and I'll see you next time.